What is a routing protocol? A routing protocol is the way routers talk to each other to share information. That's it. They discover new networks, they maintain the information, they choose the best path, the most efficient way of getting from A to B. And if that best path fails, then their responsibility to find the next one. So some routing protocols have the second best ready to go, and some of them, as soon as the best path goes away, they throw their hands up in the air, run around screaming, and then figure it out, and then say, right, here is now the best path. So dynamic routing protocols are the way routers talk to each other to tell them what networks exist and the best way, the most efficient way of moving data around the network. You could just set up your network with static routes. That's fine. Nothing wrong with that at all. But as your network grows, things start to get pretty complicated. And if you make a mistake, then, typos are going to kill you. And if something bad happens in your network, it's all static. You have to manually make a change. Whereas a dynamic routing protocol, it's dynamic. It's just constantly chattering. Routers are talking amongst themselves, telling each other what they've got. And once things are added or removed, they dynamically figure it out. Caveat is that we're going to introduce you to two routing protocols today, a bog standard basic one called RIP and a slightly more advanced one called OSPF. And OSPF is memory hungry, so it can be a little bit hungry on CPU and RAM. So if you've got a massive network running OSPF, you need some pretty decent beefy routers with CPU and RAM to be able to cater for that routing protocol. So once again, history lesson. So we've got interior and exterior. And as you can see, exterior, there's pretty much only BGP. In the interior though, there are two broad categories, distance vector and link state. Distance vector routing protocols only know what's going on based on what their neighbor tells them. So they can only see what their neighbor has told them. Whereas a link state routing protocol says, no, I need to know everything. I'm like hovering above and get a bird's eye view of everything the way this network is put together. I want to know everything. Whereas the distance vector says, no, if my friend tells me this is what's what, I'm going to trust them. Now put a little asterisk on IGRP, because if you look at the history lesson, we've got RIP version 1 and RIP version 2. We've got IGRP and then we've got enhanced IGRP. Well, IGRP is pretty old, and Cisco themselves wrote IGRP and eIGRP, but even Cisco have said, you know what, no one uses IGRP. No one should use IGRP. So it's even being removed from the iOS. So if you do question mark, you'll see it, but if you try and program it, it'll just say error. So we got RIP, eIGRP, and OSPF. They're the three routing protocols that we're going to mainly focus on, but eIGRP not so much, but RIP and OSPF, they're the ones we're going to focus on. We're going to leave BGP alone for now because that's really ISP to ISP. And in fact, here it is. So interior and exterior. Interior means inside your business. So they came up with this jargon called autonomous system. And that realistically means your corporation, your business, your enterprise. That's one autonomous system. ISPs are an autonomous system. Customers are an autonomous system. So inside your business or ISP, you can have a routing protocol, whatever you want. That's fine. Could be eIGRP or RIP, OSPF, whatever. Between ISPs, between autonomous systems, that's where you need BGP. BGP is the routing protocol of the internet. That's all we need to know for today. All right, this chart's a bit busy, and I'm sorry about that, but we'll work our way through it as we can. So we've got RIP. It's a bit slow and very, very simple. The biggest difference between RIP version 1 and RIP version 2 is that RIP version 2 understands VLSM, that lovely stuff we played with in the previous session, variable length subnet masking. eIGRP is the enhanced version of IGRP, And OSPF is super duper fast. Look at the convergence on OSPF as soon as possible. It's lightning speed. But the trade-off is lots of CPU and RAM. It needs those resources. I want to focus mostly on the bottom three rows: admin distance, metric, and routing updates. The administrative distance is the trustworthiness of the routing protocol itself. The metric is the way it understands the routes, or the trustworthiness of the routing information. So the easiest way to remember about the admin distance is that RIP was first. So they had a number between 0 and 255, so they're just right in the middle, 120. Then OSPF came along and said, you know what? OSPF's better than RIP, so we're going to beat RIP with a better number, 110. Then Cisco came along and said, you know what? Well, I reckon IGRP, that's the one. So I'm going to make ours 100. And then they suddenly realized that IGRP is actually not that great. So they enhanced it and made enhanced IGRP and made that 90. So if you've got routing information with RIP and routing information with EIGRP, then the admin distance will say, no, EIGRP is better because it's got a lower number. The metrics: RIP only understands hops, IGRP and EIGRP bandwidth and delay, and OSPF is cost, but cost is pretty much bandwidth. So we'll have a look at that in a minute as well. And just for when you're setting up security policies, RIP 1 is broadcast, RIP 2 is multicast, EIGRP is multicast, and OSPF is multicast. Now, just one little thing about RIP. Technically, it's meant to be purely periodic. It only sends information every 30 seconds, and that's that. But Cisco are a bit cheeky. And even though it's meant to wait 30 seconds before chatting, Cisco said, you know what, if something changes, we'll send out a broadcast anyway. So even though it's meant to be purely periodic every 30 seconds, then it can be event triggered as well. Okay, let us have a look at a protocol, a routing protocol, and how it actually works. I've chosen RIP because it's the simplest and it's the most easy to think about. So we've got 3 routers and we've got network 1, 2, 3, 4, and 5. So we turn on router 1. And the very first thing that happens is that it says, I have one directly connected network, C for connected. Network 1 is directly connected to my fast Ethernet, and it's 0 hops away because it's directly connected, so it's 0. Then the next thing we do is we turn on router 2. The serial link now comes up between them. So router 1 says, oh, network 2 on my serial. And router 2 says I can see network 2 and I can see network 3. Router 1 then broadcasts the entire route table to router 2. That's one of the disadvantages of RIP. It sends the entire routing table every 30 seconds. So router 1 has just broadcast its entire table to router 2 and says, hello, I can see network 1 and I can see network 2. And they're 1 hop away from you because it came from a different router. So router 2 looks at that and says, well, you know what? I already have a network 2 and that's 0. So that's better than what you've told me. So I've done some math and my network 2 is better than your network 2. So I'm just going to chuck that away because I don't need that anymore. Now, router 2 does the same thing. Bang, here is my entire route table. So router 1 now has 3 networks that have been learned via RIP. That's what the capital R stands for. So it does the same sort of math. It says, well, I've already got a network 2 that's better than what you've told me, and I've already got a network 1 that's better than what you've told me. So I'm just going to chuck those away. Now there are 3 networks, network 1, 2, and 3, and both router 1 and 2 can see all of those 3 networks. 2 directly connected and 1 via RIP. So let's turn on router 3. So router 3 has got network 4 and 5, and router 2 can see network 4 has just sprung to life. So what's going to happen here? Router 2 is going to send his entire route table to router 3. He's send him Now he's already got a 4, because 4 is better than what he has, 4 is not better than what he has, because 4 is 0, and that's 4 is 1. So we're going to get rid of network 4. But he doesn't have, that's it, he doesn't have a 1, 2, or 3. So they're all good information, so he's going to hang on to that. And of course, what does he do? He sends the entire route table on to router 2. So router 2 gets that entire route table. It says, oh, okay, thanks for that. But actually, I've already learnt about network number 1. I've already learnt about network number 4. I've already learned about network number 3, and I've already learned about network number 2. So I don't need that information. I'm going to chuck that away. The only one of any value is network 5. So the next thing that's going to happen, you guessed it, router 2 sends the entire route table to router 1. But he already knows about 3, he already knows about 2, and he already knows about 1, so he chucks it all away. And now what we have is a converged network. The term converged network is a term that means when all the routers have the same information and can see all of the network. So router 1 has got 2 directly connectors with the C, and it's learnt dynamically via RIP network 3, 4, and 5. All 3 routers can see 5 networks, and there are only 5 networks, so this is a converged network. Now, I mentioned in the previous slide that RIP is periodic. It sends the full route table every 30 seconds. If this was OSPF, OSPF is not periodic. OSPF is 100% event driven. So every time the routers come up and those links change, it would smash that information instantly. But if nothing changes, it's got nothing to say, just a tiny little heartbeat. So periodic, every 30 seconds the entire route table. Event driven or triggered, only send an update when there's a change. Now, show up your protocols, fantastic command. So first thing we want to check out is what we're running. Our routing protocol is RIP. And we've got a bunch of timers. We send our updates every 30 seconds, and the next one is due in 16 seconds. Now we've got some timers. So in case a network goes away just for a few seconds and then comes back, when we're told a network's missing, we don't just chuck it away instantly. We say, you know what? I'm going to hang on to this for 180 seconds, just in case you've gone away or you're too busy to send me an update. So I'm going to hang on to that for a little while. So that's the hold down timers. Now, like I said before, RIP's got 2 versions, version 1 and version 2. So the default is send version 1 and receive 1 or 2. We have, because it's version 1, we have to obey the class system. We do not understand classless interdomain routing or variable length subnet masking, because automatic summarization in effect. And we can turn that off if we want to, if we're doing some wacky subnetting. We are currently advertising 2 networks, 192.168.1.0 and 192.168.2.0. And currently we have got one neighbor, and that's 192.168.2.2, and we last heard from that neighbor 15 seconds ago. And the distance is the administrative distance, 120. That's the trustworthiness of the routing protocol itself. So how do we configure RIP? Well, here is our sample network. We've got a whole lot of stuff going on in here, but let's have a look at RIP itself. So the first thing we do is say router RIP, and then we advertise our networks. Network 192.168.1.0 and network 192.168.2.0. They are the 2 networks that router 1 wishes to advertise. Now this network has got some pretty funky subnetting. We've got some /30s and some /24s. So we need to enable version 2. If we don't enable version 2, RIP gets a little bit confused and freaked out. So let's make it version 2 everywhere. Now here's a new command, passive interface. As I said before, RIP broadcasts the entire route table every 30 seconds. Is there any value sending our entire route table to the switch or to the internet? No, it's a waste of bandwidth. It's just junk. They don't care about it. They're not going to do anything with it. So passive interface means do not send your broadcasts out these specific interfaces. Now, if we accidentally set passive interface 0000, then we'd be in a lot of trouble, because then router 2 would never hear from us. So when you set up passive interface, always double check, make sure your typos are correct. I mentioned previously about automatic summarization with wacky, crazy subnetting. If you are doing some pretty funky subnetting, then you might want to turn on no auto summary as well. Now the last command is one of my favorite commands, because have a look at the very top of the config. IP route 0000000 via the serial port to the internet. That is what we call our default route. That is so that everyone in this whole network can get onto the internet and update their Facebook status. Default information originate simply means get the default information, which is the default route to the internet, and I'm the originator of that. So tell everyone via RIP, hey everybody, I can get to the internet. So if you want to get to the internet, come to me. So this only R1 has a route to the internet, so only R1 needs to have default information originate. And then R2 and R3 will learn, hey guys, if you want to get to the internet, go to R1, because he knows how to get there. IPv6 is a little bit different, because first thing, remember, IPv6 unicast routing, IPv6 doesn't work without it. You need to sort of turn on RIP and give it a name. So IPv6 router RIP and give it a name or a label, some sort of identifying value. And then in the interfaces you wish to advertise, you need to turn it on in that interface. So the easiest way to remember it is IPv4 has network statements, IPv6 has commands on the physical interfaces themselves. And of course, watch for typos. You got to make sure that the name you've declared your RIP instance matches on each of your interfaces. Before I talked about the differences between administrative distance and metric, so I just wanted to spend a few seconds looking at that now. So the metric is the trustworthiness of the route itself. How are we going to get there? And the administrative distance is the trustworthiness of the routing protocol itself. So RIP. RIP only understands hop counts, and it can only have a maximum of 15 hops. OSPF understands cost. Now cost is really bandwidth. So just think about money. Just think about if you pulled out your phone and you looked at 1300 cabs or Uber or whatever rideshare you want, and you need to get to the airport, and the Uber is $60 and the cab is $50, which one are you going to take? You're going to take the cheaper one. OSPF is cost. Think about money. Which one is the cheapest cost? So the faster bandwidth is the cheaper cost. And ERGRP has a look at bandwidth and delay as well, but we're not going to spend too much time on ERGRP. I just put it there just as a reference to help you to see the differences between the thing. So RIP, hops. OSPF, cost, which is bandwidth. So the faster the link, the cheaper the cost. So super duper duper brief introduction to OSPF. OSPF is a link state, RIP is distance vector. OSPF is far more powerful than RIP because it's got a lot of extra information. It's event driven and it can see the whole network as a whole, and the convergence time is almost instantaneous. OSPF uses the bandwidth or cost as its metric, RIP uses hop count. OSPF has an administrative distance of 110, RIP has an admin distance of 120. So OSPF is more superior and admin in trustworthiness than RIP. The link, it's called OSPF link because it's a link state and it cares about the links, which is like the interfaces between the two routers. So metric is the trustworthiness of the route, admin distance is the trustworthiness of the protocol. So exactly the same network as before, but now we're chucking out RIP and we're going with OSPF. So router OSPF, and you have to give it a number. This number is like a placeholder. It's a process ID. It doesn't mean anything, but you just have to have it. Now, OSPF has this where you can give it an identity. It will magically name itself anyway if you don't, but sometimes for management and control, it's a good idea to give it an identity. So router ID and just a number. OSPF has areas, so you have to set this value. Don't worry about understanding it yet because we don't do multiple areas in this unit, but there's a few YouTube videos about it that I'll provide you with links for if you really want to understand the area process. Oh, sorry, it must be area 0. Area 0 is the default. If OSPF cannot find area 0, it will fail to function. So always in a network, a simple network like this, always say area 0. OSPF must have the subnet mask because it doesn't care the class system. It doesn't care what wacky, crazy subnetting design you've done because you just put in the subnet mask and it just works. But just for fun, the subnet mask is a mirror image of a real mask. It's the inverse. So 255.255.250, you flip it and you get 0.0.0.255. 255.255.255.252, you flip it and you get 0.0.0.3. It's the inverse of the real mask. And all the other commands are the same and do exactly the same thing. Passive interface is the same, default information originates the same. Now IPv6 is a little bit more tricky because the router ID must be set. If you don't set the router ID, it refuses to function. So turn on unicast routing, set up your process ID, exactly the same before. So with RIP IPv6, we gave it a funky name. With OSPF, we just give it a number. So just to clarify again, IPv4 network statements, IPv6 commands on the interfaces themselves. Now, the mostest bestest commandees that you'll ever need. So these 4 commands are going to get you out of jail 99 times out of 100. Show IP protocols. What is your routing protocol doing? What's it advertising? What are its timers? Who can it see? Show IP route. What have you learnt as far as dynamic, static routing? Show IP interface brief. Let's just make sure our interfaces are up. Let's make sure they've got the right IP addresses given to them. Show CDP neighbors. We haven't really talked about CDP yet, but it's a very simple command to tell you physically directly connected devices. Ideal for checking the cable. Is the right cable plugged in the right interface? Talking to the right other device. Show CDP neighbors will check you. These 4 commands are going to get you out of jail a lot of the time. So whenever you're having any sort of troubleshooting, bang, 1, 2, 3, 4. Type these 4 commands. Just do it automatically because these 4 commands are going to help you out troubleshooting 99% of. It'll find all of your typos and all your missing commands. With these 4 commands, make sure they are in your journal and make sure you use them every lab just to get familiar with the output that you'll see. So, thanks for watching. Please remember to subscribe, click the notification bell. If you enjoyed this video, give me a thumbs up and leave me a comment with what you'd like me to make for my next video. I'll see you in the next one.